These weapons were designed in the 60s and 70s and produced back then. Some of them were as much as 40 years old. The average age is more like about 25 to 30 years of age now. And you can imagine that if you had a car that old, you'd probably want to get a new one, but you can't. And getting parts to maintain that car has become challenging. They don't make them anymore. In some cases, maybe you can't make them anymore because they use materials that are no longer environmentally permitted or no longer available at all. And so you've got to sustain that car. By the way, you're not allowed to start it to see if it works. You're not allowed to test it. But it has to work with 100% reliability when you do, God forbid, ever have to start it. And so Stockpile Stewardship is the program that enables us to do that. And it has been remarkably successful. The lab's role in Stockpile Stewardship is first to surveil, check out the weapons that we have designed for the United States stockpile.
Managed by the National Nuclear Security Administration, Stockpile Stewardship relies on the development and application of advanced technical capabilities to assess the safety, security, and effectiveness of existing nuclear warheads without nuclear testing.
And we've been doing that now since the late 1990s. And to this day, we have assessed those weapons and to make sure that, in fact, the weapons that are deployed for the defense of the country are safe, secure, and effective, meaning that, should they be needed, they will work.
Folding together engineering, science, and computation, creating teams of talented people to solve extremely difficult problems is built into the DNA of the way the laboratory operates.
In fact, the weapons scientists get all the data, write the codes. What the simulation facility provides is a computer capable of running those codes, an infrastructure capable of storing the data from those codes, an infrastructure capable of visualizing the data from those codes.
That requires very fast computers. And as a result, Livermore has consistently pioneered the use of large, high-speed computers.
Sequoia is a 20 petaflop computer. That's a 20 with 15 zeros after it. It's hard to put that into perspective with the kinds of things that we use in everyday life, like a personal computer. But if I was comparing it to my personal computer today, I'd tell you it was about 400,000 times faster than my personal computer. Sequoia is going to be used for two different kinds of applications towards stockpile stewardship. The first is looking at individual science applications. For instance, materials. If you want to look at materials under certain pressures and temperatures, you can look at that at enormous scale and intense levels of granularity on Sequoia. So run a very large problem and learn new things about the way that material behaves under different constraints. Okay, so that would be running a code at a very large scale so that you could see things you'd never been able to see before. The second thing, and a very important part of the Sequoia mission, is something called uncertainty quantification. And that's actually running large numbers of smaller jobs and turning the knobs on these jobs to look at the margins of uncertainty. And so what you can do with a computer like Sequoia is you can run large numbers of these suites and then inform the next suite with the answers from the previous suite. And what you're really doing is advancing the pace of discovery on these problems.
In addition to its mammoth computational power, Livermore has an array of unique facilities which allow the laboratory employees to be nimble in the ever-changing needs of stockpile stewardship.
So the Superblock is unique because it has a wide range of capabilities in a very small area, basically one city block. What is particularly unique about our operations are our people. That we have a mixture of PhDs, of scientists and technicians, everybody working side by side to make sure that everything's done safely and compliantly. We are able to be nimble and respond to changing mission very quickly. In the plutonium facility, Building 332, it's a Category 2 nuclear facility, which means that you can have special nuclear materials up to certain limits in that facility. And we do aging tests on plutonium.
This small quarter-sized plutonium target, developed here at Superblock, is being prepared for an experiment that will take place 400 miles away.
Five inches remain, pointing the target. 4 inches remain, doors are locked, lights are active. 3 inches remain. PI, are you ready for pin power? Slow down, and we're docked.
Attached to a target assembly and loaded into a chamber, this target is about to be impacted by a projectile moving at 8 kilometers a second, 8 times faster than the speed of a bullet shot out of a rifle. The lab's rifle is a 2-stage gas gun called JASPER.
JASPER, Joint Actinide Shock Physics Experimental Research. Since its first experiment on plutonium in 2003, JASPER has performed over 50 experiments on plutonium, and each one of those points has provided insight to the entire nuclear weapons complex about important ways in which plutonium behaves. One very important question JASPER has been able to contribute to is the question of plutonium aging. Since the end of nuclear testing, we have to keep weapons around much longer than we'd anticipated keeping them. And if plutonium ages in a way or deteriorates in a way that would shorten the lifetime of these weapons, that would be a fundamental flaw in our stewardship strategy.
Scientists shoot a projectile at a plutonium target and study the shock data produced at impact. Results from these shots have already produced huge returns.
With that data, we were able to put together plutonium aging models that showed us that there was not a significant impact to weapon performance over decades of plutonium aging, and that was part of an important decision not to go forward with a very expensive pit production facility.
This is HEAF.
HEAF, the High Explosive Application Facility, is the R&D center for explosives research at Livermore. And in that facility, we do all aspects of explosive research and development, from making explosives to characterizing them, measuring their properties, measuring their aging properties, their detonation properties, their safety properties, anything you need to know about the material. And then we also can detonate them, we can blow them up. Explosives are a key component of the nuclear weapon, and where we are today is we have a series of nuclear weapons that were designed for a 10 to 20 year lifetime 20 to 30 years ago, and we're being asked to certify them for another 20 or 30 years. And so the explosives, because they are such a critical part of the device, and because they do change over time, we have to understand very carefully how they change and therefore how they might affect the functioning of the future stockpile. The HEAF is a unique facility in the country and in the world, as far as I know, in that it has all the aspects of high explosives research and development under one roof. The synergy of HEAF, the efficiencies of HEAF, are twofold. One is all the activities are together, so you don't spend time traveling, you don't spend time shipping explosive on public roads or otherwise from one location to the other. Perhaps more important is the fact that because the chemists and the detonation physicists and the diagnostics scientists all live together and they share the same coffee pot and they share ideas on a daily basis. And so great ideas come when people work together and think together.
At Site 300, we execute a number of experiments to support that mission, to support maintaining the nuclear deterrent.
Hydrodynamic tests are conducted at the site's contained firing facility. Explosive detonations using up to 60 kilograms of high explosives can be conducted in this modern test facility.
CFF is a very large bomb chamber compared to most bomb chambers people think about. It's 50 foot by 50 foot, 30 foot tall, with amazingly thick reinforced concrete walls. It can handle up to 132 pounds of high explosives in various configurations. These are typically experiments that are in a weapons geometry, sometimes the exact weapon geometry, but with the nuclear material removed. And so they have no potential for making nuclear yield, but they allow us to test the configuration and understand things better, but they're obviously large charges of high explosives. Equally important to the nuclear deterrent is the confidence that the country and our allies and our adversaries have that if something were to go wrong with the deterrent, or if we needed a different flavor or aspect of the deterrent, that we have the capability to address that issue, either that issue or that need. And that's a combination of the capabilities, some of which we have at Site 300, and in the infrastructure, but just as important, the people. We have to have the people knowledge and the people skills and capabilities to either address the issue or address the need.
In contrast to Site 300's massive detonations, Livermore's National Ignition Facility, HEAF, creates implosions on a minute scale.
And so what you do is you start with these beams at the size of about 40 centimeters across, and they get brought down and focused down to less than 1 millimeter across. Their precision is phenomenal, about half the width of a hair, the precision of the accuracy. And they fire all these 192 beams into a very small volume, hitting targets that are millimeter size, high precision, very carefully made targets. And by focusing so much energy into such a small space, what they do is they can get to temperatures which are equivalent to the temperature at the center of the sun, and pressures which are about 1 billion times what the Earth's atmosphere is. And so these are conditions that are relevant for weapons performance, and so it pulls it all together and allows us to explore that kind of physics space which we really care about when trying to answer questions for the stockpile stewardship.
Shot director, ready for shot.
What HEAF does for us is it provides us data, and we use that data, that experimental data, we use that to validate our simulation codes and the physics models within our simulation codes. And then it's those validated codes that we use and apply to stockpile stewardship problems day in, day out as part of the stockpile stewardship mission. So that's, in a way, that's quite similar to the old days, where we used to use our UGTs to calibrate our codes. Today we use HEAF and other facilities to help validate our codes and apply them. Finally, it helps us to develop the expertise in our people, who are really the foundation of the nuclear deterrent. And I'd say all those last 4 aspects were also a very key part of the underground test program. So in that sense, I would say yes, HEAF does in many ways replace many of the aspects of the UGT program.
Throughout its 60-year history, Lawrence Livermore National Laboratory has been dedicated to solving the nation's most pressing scientific and technical concerns. Through its contribution to the nation's stockpile, and now to the nation's Nuclear Security Administration's Stockpile Stewardship Program, it will continue to be a leader in ensuring the safety, security, and effectiveness of the nation's nuclear deterrent.
We are taking better care of these weapons today, I believe, than we were when we were doing nuclear testing. We understand them better today than we did back then, because we have to, because we can't test them. And I think it's a huge success.